Hierarchical modeling is a method of making complicated models from simple primitives. In computer graphics, we often need to make models that are a little bit more complex than simple spheres, circles, and rectangles. A complex object can often be decomposed into simpler primitive parts. We will refer to these primitive parts as symbols. To render a complex object, we can transform these parts separately to fit the object. We must define an instance transformation for each part. We put the word instance in front of the transformation to separate it from transformation of the complete object. For example, a cylinder of radius 1 and height 1 can be scaled and then transformed in different ways, for example, to make the hand of a robot. Now we can scale, rotate, and translate this same symbolic object to form a different limb of the robot. And if we continue this process, we will be able to make more complicated objects. The instance transformation follows these steps. First, a scaling is applied, then a rotation is applied. In fact, we can apply the rotation first and then the scaling. But generally, the convention is to scale the object to the required size and sometimes we can also apply a shear transformation to it before we rotate the object and then translate it. But if you recall from your transformation lectures, rotation must be applied first, and this should be followed by the translation. This is because all rotations kind of happen about the origin, and hence starting with the model, the symbolic model itself, we are already at the origin, so we might as well apply the rotation first and then translate the object. In OpenGL code, we initialize two matrices. One is for instance transformation and one is the model view matrix. And then we calculate the instance transformation by first applying scaling. Remember that these matrices are applied right first because this is where your points would lie. This is where your variable of containing XYZ coordinates of the points would be. So this is scaling, then rotation about x-axis, y-axis, z-axis. We can apply them in different order to achieve a desired rotation, and translation is the last one applied. And once we have this instance transformation matrix, we can use it to change the model view matrix and update the model view matrix, and that is the one that is passed on to the vertex shader. This could be applied to cylinders or to any other object. These instance transformations are stored in a table. For example, for the example before, we would probably have 8 different instances of the cylinder to represent the left, right, upper, lower arms and legs of the robot. For example, this is the torso of the robot, so we will have upper leg, lower leg, and then the left one, upper leg, lower leg, and then for the arms, upper arm, lower arm, upper arm, and lower arm. So 1, 2, 3, 4, 5, 6, 7, 8. So these are the symbolic cylinders, and we have created 8 instances of these cylinders, each one following perhaps a different scale and definitely a different rotation and translation to take it to the required place in the complex model of the object. We probably would have another cube as a head, or maybe 2 instances of the same cuboid here, but in here perhaps 2 is the symbol 2 is the torso of the robot, and the symbol 3 is the head of the robot, and the limbs are represented with cylinders. So we can store each symbol instance into a symbol table for the complex object by assigning a number to each symbol instance and storing the parameters for the instance transformation. So this refers to which symbol we are referring to, and this is the cylinders that are used for the limb. And notice that the cylinders have been used multiple times because they appear multiple times in the complex object shape. And this table will have the details of all symbols used any number of times and their respective scaling, rotation, and translations to fit into the more complicated object shape. Right. So now we know how to make complex models from simple shapes by translating them, scaling them, and putting them at the right locations in the complicated object. For example, if you were to model a car using the symbol instance table, we would have 4 instances of the wheel, 1 instance of the chassis, and then we're good to go. However, there is a problem with the symbol instance table, that it does not show relationships between different parts of the complex model. In this example of the car, the chassis plus 4 wheels also have some relationship. That is, the rate of forward motion determined by the rotational wheel speed of the wheels is not taken into account by the symbol instance table. So the chassis has to move at a certain speed that is determined by the rotation of the wheels, and the rotation of the wheels should also be consistent with each other. This wheel cannot rotate at one speed, and this wheel cannot rotate at a different speed. To solve that problem, we will need a different representation. Now consider the pseudocode for the rendering of the car. That might look like this. We initialize a variable speed as a float, direction, that is a 3-dimensional vector, and a time t variable. Then we'll draw the right front wheel, the left front wheel, and so on. Continuing this process, we'll draw the 4 wheels, and then we'll finally draw the chassis. Right, so the chassis. Now this pseudocode fails to show the relationships of the different parts of the car. For example, the wheels do not rotate independently, and the chassis must move together with the wheels at the speed that is determined by the rotation of the wheels of the car. The question is, can we use a graph to represent the relationships? So we need something that would represent the relationship in the hierarchical model, and in a way that we'd be able to use that relationship to determine the relative motion of these objects if you were to animate the object. So graph is one of the competitive representations. A graph consists of a number of nodes and edges, so it's a very simple representation. The edges are also called as links. An edge connects a pair of nodes, and we can have the edges as directed or undirected. So in a general graph representation, you could have a directional graph or an undirectional or an undirected graph. Another case is a cycle graph, where you have multiple paths, this is connected with this, but this is again connected with this, and this is connected with this. So this is called a cycle graph that has a directed path which forms a loop. Another type of graph is a tree. A tree is a graph in which each node except the root has exactly one parent node, but they may have multiple children. So starting from one parent node, you can have, say, 2 children of the parent node in this case, and this child then has further 2 children, whereas this child has one child of its own. And the final nodes that do not have any children are called as leaf nodes. And this, of course, this terminology resembles the terminology of the trees, where every branch sort of branches out to multiple children and they end up on leaves. So leaves do not have further branches. Now we use this tree model to represent the model of the car. So we have chassis as our root node, and then it has 4 children, the 4 wheels of the car. Another possible way is to have a DAG model, which is a directed acyclic graph. This is not much different than the tree, but in this case the representation goes like this. So we have one wheel, but we have sort of all four edges connecting the chassis to the wheel. So how do we use these graphs in computer graphics? Well, they're useful for moving the complete object. They're useful for animating parts of the object. How exactly? This we will see in the next lectures.